Okay, so to try to get this presentation started on time, I'm going to ask everyone to turn off your phones, please, or any other devices you have that make lots of noise. And also, please remember at the end of the whole thing to fill in the questionnaires. We'll just wait a few more seconds for the people to come in. Okay, I'm going to get started here. Feels like there's, yeah, that's better. Okay, so welcome everyone to my talk, Parallelizing the Naughty Dog engine using fibers, or as it was at one point called, more fiber to increase throughput. But that was not okayed. Anyways, my name is Christian Yearling. I'm a lead programmer at Naughty Dog, and I've been there for about 8.5 years, so basically the whole PS3 cycle, starting with Uncharted 1. What we will be talking about today is basically how our engine evolved from PS3 to PS4, and more specifically focusing on the Last of Us Remastered. We will talk about how we're using fibers for our job system, and we will also talk about what we had to do to really utilize the cores on the machine. So to give you guys a background of where we came from and how our PS3 engine was architected. It was a single-threaded engine. It was basically running at 30 hertz. We never had a 60 hertz engine. And all the game logic was executed first, followed by command buffer setup and kind of render logic. Then we kicked off the render frame that would actually execute on the GPU. The SPUs were used as worker threads, so most of our game systems were offloading work onto the SPUs, and we used them quite heavily. There was, however, very little gameplay running on the SPUs. There were a bunch of restrictions. You had to bring up all your code, so code size was a big issue, and it was pretty messy to try to run jobs that didn't actually run to completion. So that was one of the biggest issues we actually had with the job system. It's not always feasible to take a particular task and actually break it up into atomic units that need to finish. Sometimes you would want to run the task halfway through, offload a little more job to some other cores, and then continue on. That was not possible with our old job system. The user also had to do a lot of management. I'm just going to put both of these up. Basically, the user of the job system was the one that had to allocate arrays that were actually being accessed by the SPUs. Because of the complexity and the ease of accidentally having stale pointers, we ended up with just massive amounts of globally allocated arrays for probably about 100,000 jobs. So that's a big waste. The state of a job list, which was the means of how you submitted jobs to the system, was very confusing. It could be running or it could be stopped. You didn't really know. So when you submitted a job, it could immediately start running on an SPU, or you would have to kick it later. So depending on what had been done before your code, you would have different execution patterns. We wanted to try to avoid that. Synchronization was also a little bit messy. Arrays was the means these job lists were built from. To get any kind of synchronization, you would introduce job markers, which was basically just an index in one of these arrays. The problem with that is obviously once the array is full, you can't reuse that same index again unless you clear out the whole array, which would cause stalls. So yeah, it was kind of messy to deal with those. So we really wanted to solve some of these things for the new job system. The main thing was we wanted to allow jobifying our entire engine, like no exceptions. We wanted to be able to yield in the middle of execution. This was a key thing to be able to jobify something as complicated as Drake. So the example here is the player needs to, for example, do some synchronous leg ray casts. We need to be able to do that in the middle of a really deep call stack and not have to try to kind of cut the work, then get back later. We also wanted it to be really, really easy to use the new API for the programmers. And definitely no memory management. That goes with the ease of use. We also wanted just a very, very simple way of synchronizing objects. Not one, or not like 2, 3, or 4. There should be one, and everyone should be able to really wrap their head around what's going on. Performance was secondary. So when we started out with this, it just happened to be that fibers are actually really performant, but that was not the main reason for doing this. So what is a fiber for those that maybe haven't used them or aren't too familiar with them? Well, it's basically like a partial thread. If you think of a thread as containing stack space for execution of your code, it contains space for saving off registers once the thread actually goes to sleep. And it also contains a bunch of other stuff that the system needs to be able to schedule the thread, priorities, affinities, that kind of stuff. A fiber is only the stack space and the space to save the registers. So the OS does not know how to schedule these things at all. It is, however, executed by a thread. So what you can think of is you take your normal thread, and all you do is you swap out the stack pointer and basically your program counter. That is what switching a fiber means. Fibers are cooperative multi-threading. What it means is a fiber can never be preempted. Because it basically acts like a normal function, switching fibers is just switching stack pointer and registers. There is no such thing as a fiber interrupting another fiber. You need to explicitly call yield, or in this case, ski fiber switch, which is the PS4 function. Because it's so simple to switch these registers, switching from one fiber to another, or basically switching from one task to another, is extremely cheap. All you're doing is you're saving a couple of registers, effectively swapping out your stack pointer and a few other registers there, and you're off to the races. The OS doesn't even know you did it. So how are we using this in our job system? Well, we have 6 worker threads. Each one is locked with affinity to a given core. Each one of these threads is what we call the execution units. They never move. They are the vehicle in which the jobs actually execute. A job itself is effectively a function pointer. That function pointer is getting called from within a fiber. The fiber is the one that provides the stack space, and therefore the execution environment. The only way we have to synchronize is using atomic counters. Why we're using atomic counters, I'll explain in a little bit. We have 160 fibers. What that means is we can have 160 individual jobs that haven't completed yet. We have 128 that is what we call the small stack. That's from your normal kind of a leaf node type of work, where you do a little bit of a job, but you always complete it. It's your normal task. Then we have a couple of really big ones where we call out to middleware or various things that we can't really control the stack depth. We are not very sophisticated when it comes to trying to avoid synchronization, or not synchronization, contention when it comes to job priorities and job queues. Instead, we made it very, very simple. And we said we have 3 global job queues, low, normal, and high. What the #1 goal of the system was, if any thread push a high priority job, that should be the next job running. I know there are other like job stealing kinds of job systems, but we wanted a different approach for, we didn't want throughput to be the number one deciding factor. We wanted immediacy and kind of very controlled execution. So at a very high level, this is how our job system looks. Jobs on the right, into the job queues, 1 out of 3. You have a bunch of fibers in the middle, and on the left, there are 6 worker threads, and I'm trying to illustrate that the fibers are executing inside of a thread. So if we go through a quick little example how this works, you got a fiber, which I will just use that term from now on, but it is basically your stack space. So fiber is executing, it will pull a job from the job queue. At any point, it's obviously allowed to add more jobs to these global job queues, and we always push them to the end. If you're now running into a condition where you need to wait for one of these synchronization counters and it doesn't have the value that you expect it to be, we will immediately move the fiber over to a wait list. We will also associate it with the counters. In this particular case, the yellow job here wants to wait for the counter to become 0. It's not that yet, so we take the entire stack, including the registers, and basically it's like taking a snapshot, move it off to the side. To be able to continue executing other jobs, we now pull a new fiber, a new stack space for another job to start executing in. We pull another blue job, and in this particular case, when the blue job completes, we have the option of associating an atomic counter to be decremented when the job finishes. In this case, the blue job was actually the one that was the dependency for the yellow job to continue. The counter gets decremented, the yellow job is now allowed to run. What happens at that point is the worker thread realizes that I need to resume an existing call stack. It then returns the fiber to the fiber pool, effectively just switches out program counter and a few registers, and resumes executing the yellow job. So a few more details about the job system. Like I said, the jobs are locked to cores. Main reason for this is we noticed that we have 6 cores that are exclusively for computation. That's basically what we do with them. What it means is that they will run for a very long time uninterrupted on every core. When, and it does happen all the time, the kernel threads or some other thread come in and evict us, what ends up happening if you don't have cores locked or threads locked to a core is that, let's take the example of core 0 gets interrupted. The thread goes out, says, hey, I need to run somewhere else. All of the other threads are going to say, well, I've been running for a very long time. Why don't you take my spot? So you end up with actually a ripple effect across all your cores. This means that you will actually have, at the very least, 6 context switches every time you have a kernel thread that comes in rather than just 1. So this is the function that we're using in our job system, the one that the gameplay coders see. It's just a wait for counter, pass in the counter and the expected value. When this happens, counter is checked. If it's not what you would expect it to be, the job sleeps, and the code doesn't even know that it gets transferred in the background to a wait list. In The Last of Us Remastered, we have about 800 to 1,000 jobs executing this way at 60 hertz. So everything is now a job. We were able to actually jobify the entire engine to the point where we do not have a main thread anymore. There is a tiny, tiny little job whose only job it is to spawn the initial job that will actually at the end create a frame. So there is nothing that kind of drives the whole engine or pumps it. It's more or less like a normal operating system. We do this except for one thing, I/O threads. So the thought with the job system is that we want to utilize the cores as much as we can. We therefore ban any calls to blocking functions. So that usually includes things like dealing with sockets, dealing with file I/O, anything that where the kernel will kind of block us and put us to sleep. For those cases, we have special threads. It's actually normal system threads. They will sleep almost 100% of the time. When they wake up, because there's some data coming in, we take that data, put it in some global storage, kick off a job in our job system to start processing that data or get scheduled to process the data and immediately go to sleep again. So when these come in, they're really more like interrupt handlers. Very, very quick in, out, and that way the job system behaves very nicely. So this is our in-game profiler. We will see it a bunch later, so I thought I'll just do a quick overview of what it is that you're looking at. On the left, we have our 6 cores. For each core, the first row is the individual jobs. So there's one tiny little block per job. Under that is the call stack for each one of those jobs. So if something goes to sleep, we basically will depict that as effectively a sharp edge. But when it wakes up, it will be at that same depth, if you will. So to give an example of how easy it was to now transition our engine for an average gameplay programmer over to the new job system, I'm just using this simple example of animating 100 objects. The traditional way that we had, let's say, is you call the function. It will loop over 100 times the animate object function, every time passing in the pointer to the object that we're animating. Like right here. So instead of doing that, we've now rewritten this function in just a small way. You can actually create the job declarations on the stack. This was a very big thing of trying to make it easy for programmers to not have to deal with memory lifetime, memory management for the job system. So effectively, you create all your job declarations, function start pointer, and argument. We fill it all in. And we have had to do one small little change, which is the function to actually animate a particular object. Now just have a simple little job entry point macro. That's really just to make sure that the parameter isn't forgotten when the programmers make this function. Once you've created your array of 100 work items, you call run jobs, pass in the pointer to your array, say that there's 100, and you will get an atomic counter back with a value 100. At this point, all the jobs starts running in the job system, and you can wait for the counter to become 0, and when it is, you can free it. The reason for the and free is sometimes you don't want to free. You want to reuse it over and over. But this is kind of the simplest way to jobify a whole bunch of code. So this is actually how this example would execute. You have the colored job. This is the animate all objects. It will spawn 100 small jobs that will execute. While those are running, it is actually sleeping, waiting for the counter to become 0. For every one of those jobs, when they complete, they will decrement this atomic counter. And when it reaches 0, the animate all objects job will wake up. So if we kind of look at this and criticize the system a little bit, let's talk about the pros and cons. So definitely a pro is that it's really, really easy to jobify our engine. It did not take many weeks for our entire programming staff to jobify the majority of our engine with this. It's really easy to synchronize our jobs because we can use this wait for counter. You don't really need to know about semaphores or various barriers. It's always this thing. That's the only thing you need to worry about. And it happens to be that they're super lightweight. Like I said, the initial thing was to solve a very, very high-level problem. We wanted to make sure that we can use all the cores. We want to make sure we can jobify everything. The fact that it's actually just I think it's around like, I'm not going to say the exact number. I would guess it's about 2,000 cycles maybe to make a switch from one fiber to another. So there's obviously, with something good, there's got to be something bad. The main thing that's bad with fibers is that you cannot use any of the system primitives. You can't use mutex, you can't use semaphores, you can't use condition variables, because the OS will tie those to the executing thread. Fibers, which is just a call stack, can get switched over and actually be continued executing on any of the worker threads. What ends up happening if you take and lock a mutex, you go into your critical section, you sleep on a counter, for example. Once that counter has been satisfied, any of the worker threads can continue executing this particular call stack, which means you will never free the mutex and you end up in a deadlock. So we have an abstraction for system primitives, most engines do, and we just prevent jobs from ever calling it. Because of this, we need to have our own synchronization methods. So synchronizing is done on the hardware level. We're using atomic counters. And in very special cases, when you need to have locks held for very long periods of time, we have a special, what we call a Naughty Dog job mutex, which effectively uses the job system to go to sleep rather than actually spin locking. So what support is there for fibers? It's obviously something that not everyone's used, and there's been a reason for it. In the past, fibers haven't been very good supported in various debuggers specifically. But right now, speaking for the PS4 debugger, they are very well supported. A fiber can be viewed just like a regular thread. It shows up in your thread view. You can inspect the stack for any one of the 160 fibers we have. You can see where it is, what it's doing, what it's waiting for. It's very nice, actually. You can name and rename fibers. We use this to indicate very quickly when you're kind of scanning over the thread view. We rename fibers that have started executing a job, and we rename it to the name of the start function. So you will see that there will be an animation update job and maybe a physics update job. It's very, very handy. Crash handling was a big thing that we have actually personally worked with the kernel team a lot to make sure that when the PS4 crashes, the OS is aware of all of our fibers, and it will save all the various call stacks that are actually active so that you can properly debug core dumps when you get them back to your studio. There's one issue that I want to mention before you guys all start using fibers, because I know you will do that after this. There is an issue called fiber-safe thread local store optimizations. What this is that currently all compilers have this, are allowed to optimize accesses to TLS. What it means is the first access in a function, the compiler is allowed to store and save off the address for where this thread has its variables stored. What happens is if you actually yield or you do one of these fiber switches, when you wake up, the compiler will execute code that has stored on the stack a pointer to a different thread's TLS. I know that the Windows compiler has a fiber-safe optimizations flag. Clang currently does not have that, but we have a workaround which basically means every time we're accessing thread local storage, we have the accessor function in another CPP file. It's a little clunky, but you almost never call these things, so we haven't really bothered to even try to do something about it. Even though I said don't use mutaces or any of the system primitives, there's one key location where you absolutely need to use them. In the job system, we allow regular threads to post jobs into the job system. Like I was saying, you have one of these interrupt handlers that come in, read some data, post a high priority job, in our case, audio update, for example. If you do that, it's very, very possible that you preempt a thread that's currently holding a spin lock on an atomic variable. This higher priority thread that comes in is trying to acquire that same spin lock to post a new job into the job system. This will never resolve because the thread you kicked off is locked to the core that you're actually running on. The way to solve it, or the way we solved it, is we're using what's called adaptive mutexes. They are effectively doing a spin lock first, trying to acquire the lock. If it can't, it falls back to the normal system call, which is just acquire mutex. The reason for doing this is the OS has a feature called priority inversion, which means that the lower priority thread can, in certain circumstances, actually execute before a high priority thread if the high priority thread is actually waiting for something that the low priority guy is holding on to. Putting this in solved all of our outstanding synchronization problems and deadlocks in our job system. So let's compare it to other job systems. Why did we do this in the first place? Well, one of the most popular ones that's being talked about is Intel TBB, or thread building blocks. It's got a very rich feature of mechanisms for synchronizing jobs, for creating job graphs, sequences. But as soon as you need to wait inside of one of these jobs for another one, you will need to pay the cost of a context switch. If you don't want to do this, some job systems do kind of a nested job approach, where as soon as you're pretty deep in your call stack executing a job, trying to test for a counter, it's not the value you want it to be, instead of switching to another thread to incur that context switch, it will pull the next available job from the job queue and start executing it. The problem now is you start stacking your jobs on top of each other, and the bottommost job can never start or can never resume executing until everything above it has unrolled. None of these problems exist with fiber-based job systems. Okay, so let's move on. We have our job system. We have our PS3 engine. Let's actually convert it over to PS4. So to give you an idea of how we approached this, we wanted to make it very easy for the programmers to know whether or not we were approaching what we need, where we needed to be. We set out the goal that we wanted the Last of Us to run at 60 frames per second. So we created a green area. If the frame completes in the green area, we're running at 60. If the frame completes in the blue area, we're running at 30 frames per second. If you're in the red area, it's time to really start stepping it up, because we are running sub 30 and we're pretty darn far from where we need to be. Well, this is how we looked when we moved over to the PS4. We're running way below 10 frames a second. We have jobified everything that was jobified on the PS3, but we have a completely new rendering engine. And none of that has, at the current stage, been jobified. So let's do that. Now we've jobified everything. We definitely got a big speed up. We had 130 milliseconds. Now we're down to 55. But we're still way, way, way in the red. Well, let's keep working on it. So we kept dealing with the use of locks, removing. We had enormous amounts of locks in our engine that we thought we needed, and they just caused deadlocks. Instead, don't kid yourself. Locks is not always the solution. You really need to look at your data flow of the engine, try to remove those locks. So we got a pretty big speed up by jobifying some more, being smarter with how we're using locks, and we got down to 36 milliseconds. Not quite 30 hertz, but we're getting there. One thing to note here is this is April 8th. We shipped the first week of July. So this is 3 months from shipping. And we're not even running at 30. There are a lot of people that were scared at this point. Well, we put in another couple of weeks of optimization, and we got to basically this state. We're 25 milliseconds for a frame. We're running at 30. We could ship. We wouldn't run the way we wanted to, but at least we're having a solid 30 hertz. One thing we realized at this point is that we've jobified pretty much everything in the engine. We've spent quite a long time just seeing what's wrong with it. The GPU optimizations on the new rendering engine is going pretty well, and we're not really expecting that to be what's going to prevent us from running at 60. But we're CPU bound, and more specifically, the critical path is what's taking 25 milliseconds. We've jobified so much that there are these atomic blocks that we can't actually break down anymore. But there's lots of holes on the CPU cores. We're not really using the PS4 very well. And at this point, we're only 2 months away from shipping. With the current rate of increasing our frame rate, we will not hit our 60 hertz goal. So let's just take a look at the frame for a moment. There's tons of small to big and medium-sized gaps in here. We obviously want to fill them and try to compress the frame down. As I said in the beginning, we're running game logic first. That was the way the PS3 engine worked. So we're running game logic here, colored in green, followed by the command buffer generation and various render logic, colored in red. Well, so we sat down. We took a bunch of the engineers and we sat down and said, what should we do? Should we just say we're going to run at 30 hertz? Should we try to go for 60? If so, what's the plan? Well, if you actually calculate what's going on, we have about 100 milliseconds worth of work. That is 25 milliseconds for one core. We have 6 cores, that's 150 milliseconds, but we have a whole bunch of gaps. So it's about 100 milliseconds worth of work. If you take those 100 milliseconds, you divide that across the 6 cores, it magically turns into the number 16.66, which theoretically means we're running at 60 hertz. Okay, so it's theoretically possible, but how do we do that? Let's just cut it in half. Let's not run the whole thing. Well, what does that mean? So the current design is that we're running, like I said, game logic first, rendering logic second, and the most natural thing that probably most of you guys are thinking is, well, spawn another thread, have that processing kind of like render logic in parallel. That will do it, right? Our new design is instead of running game logic and render logic completely in parallel, but processing different frames. So we changed our engine to start processing a frame in stages. We have a game logic stage, render logic stage, and GPU stage. When the first frame has completed its game logic execution, we pass it on to the second stage. Start processing frame number 2 in the first stage. So on and so forth. So each stage is now running by itself. There's no synchronization needed, and the stage can process the next frame as soon as it's done with the previous. Complexity in the engine is simplified a lot. We're basically now thinking about stages instead of frames. So this is the old design. As we were seeing, it's the same picture we had before. Here's the layout with all the game logic and render frames. Here are all the holes. And what happens when we start running these two things in parallel? This. We are suddenly running at 15.5 milliseconds. Ship it. We're done. This happened just 2 months before shipping. Once we got this on screen, we know we could do it. So that was pretty much one of the biggest changes we did for the engine. So let's go over and talk about what happens when you start doing this. What's the implication of running multiple frames in parallel? Well, you need a little background. So memory allocation on PS3, we try to never, ever call delete on pointers. So we use linear allocators, basically anything in a frame that we create, skinning matrices, data that we need to feed to later stages like camera positions and stuff like that. We allocate them from a contiguous block of memory with just a simple offset. Every allocation increases the offset. When the frame is done, we set the offset to 0, effectively getting all the memory back to the system. We also had single, double, and triple frame buffers. This was for kicking something off one frame, picking it up the next, or kicking something up a frame that was going to be consumed by the GPU. There was a lot of hand-waving when it comes to how long does memory actually have to live before getting consumed. This works great as long as you have a single frame in flight. So what we started running into was lots of these questions. When should I free my memory? How many buffers do I need? Which buffer should I index? What's my delta time? And every programmer for every single system tried to solve this. Skinning matrices, for example. Well, the animation system would say, well, this is for the GPU, so I need 2 buffers. Or is it 3? I'm just going to make it 4. And all the systems basically started over-allocating memory because there wasn't a clear concept of what the engine started doing. It was really hard to understand what was going on, and like I said, lots and lots of bugs came from this. So it's all this talk about frames. It's really hard to actually have a conversation in our industry talking about frames because everyone has a different understanding of what a frame is. What is it? Is it a game logic frame, a GPU frame, a displayed frame? Don't get me started on Maya frames. When can you actually free memory to not sit around and just hog these massive amounts? What does a frame mean? But we need a new way to just get on board of what is a frame. And I'm not talking about you guys. I'm talking about for us as a team at Naughty Dog, we could not be on the same page of what that meant. When do you need to free your memory? So this is our new definition of what a frame is. It's a piece of data that is processed through a series of steps to ultimately be displayed on the screen. The key point is it's a piece of data. It's not a measurement of time. It can take however long to take a single frame and go through all the various stages to, in the end, be done to be presented on screen. But that's not a measure of time. That is an image. So basically, frames per second is how many of these can you get done. It's a measure of throughput, not the measurement of time. So we define it by a frame. We define it by the stages it goes through. So to simplify the handling of this, we introduced something we call frame params, or frame parameters. It's a data structure that we allocate a unique instance for every single one of these frames using our definition. At the very, very beginning of the frame, we seed it with whatever the delta time is. And from that point on, it starts flowing through the system. It contains the frame number, the delta time, any data that gets generated that ultimately will contribute to displaying this frame on screen is added into this structure. So it's kind of like your globals, if you will, put into one structure and made a unique copy for every frame that you process. Because as you start updating multiple frames, your global delta time variable, everyone will read it. You will not get the right value. HUD is going to start flickering. Things go wrong. We use this as the entry point for every one of the stages that I mentioned before that a frame passes through in our engine. The really good thing about using this approach is suddenly this structure is an uncontended resource between multiple frames executing in the engine. No other frame that's executing will have access to this data structure. So you know that you can access all the pointers freely. There's no locking going on. You don't need to have some index in mind of knowing how many buffers, how many frames are going in flight. All you have to care about is I'm dealing with frame 14. I'm going to look at the frame parameters for frame 14 and pull the skinning matrices from frame 14. We also put the meshes in here. So to allow rendering to progress naturally, we snapshot all the pointers to all the meshes that we want to have visible for a given frame. That way, when you start going into debug menus or triggering various visibility volumes, we always send the correct number of meshes through to the system. For various reasons, we also have the start and stop time of every stage. This is really useful to know when was a stage done. And the reason why this is good to know is you usually create data from one stage to be consumed by another. We have a really simple function just called hasFrameCompleted. It is basically just going to check the timestamp for whichever stage that you're interested in querying. In this case, it defaults to the whole, like all the way to the end of GPU execution. So if you call this and it returns true, you know that you can freely free all the memory that has been allocated for skinning matrices, any kind of GPU consumed data. This was what we were missing. We needed a simple way to track when we can free memory, and this was really it. We have 16 of these parameters in our engine, which means that we can go back 16 frames. We can see how long did these various frames take. Obviously, we don't have 16 frames worth of memory allocated, so once the frame has been completed, the pointers that exist in this particular data structure are considered stale. They have been returned to the system and are now currently being reused by another frame being processed. So now we have the same picture as before, but we're actually passing through these frame parameters through the system. They are the blocks that define what is being processed, where is it being processed, and a frame is now very, very clearly defined by the stages it's going through. And you can ask if a stage is complete and if you need to free the memory. But we have a lot of memory. We have a lot of stages. 3 might not sound that bad, but as soon as you start saying you have memory that gets allocated and consumed within one stage, you can pass it from one stage to the same stage but the next frame. This is what we do for low priority raycasts. You can feed things to another stage, like these are the meshes that I want to render. Or you can feed it to the GPU, our case with the skinning matrices. Here, use these for skinning. And then you have onion and garlic, our CPU and GPU memory. So we basically have 10 different allocators. The problem with this is we quickly run out of memory because all of them are allocated for worst case. You will crash sometime, start increasing the size of this buffer. Crash somewhere else, you increase that one. And at the end of the day, we were sitting with hundreds of megabytes of wasted memory just there for a particular allocator to kind of not crash when it had a little spike. So we came up with something we called a tagged heap. This is a block-based allocator. We're using 2 megabyte blocks because that is the large TLB size for PS4, which basically means slightly higher performance on CPU. Each block is owned by a tag. This tag can be whatever you want. In our case, it's a 64-bit value, and it does not support free pointer interface. Instead, you allocate blocks by associating them with a tag, kind of put it on my credit under bill, and at the end of the day, you say free all blocks associated with this tag. Under the hood, this is just implemented with a simple bit list, so freeing all blocks is nearly instantaneous. So this is kind of how it looks. We've got a tagged heap on the left. All of these blocks are 2 megabytes. On the right, you got an allocator currently having a 2 megabyte block tagged with a game tag. The other blocks on the left, we got a tag called GPU, game, and render. So when memory requests are coming in, the allocator will use its local 2 megabyte block to service those requests. When it runs out, it will go back to the back end and say, hey, I would like another memory block. Put it under the tag game. It returns it, everything is happy. And at the end of the frame, or in this case, when we can say a particular stage has completed, I'm now okay with freeing all that memory, you say free that tag, and all the memory is freed at once. So this is really good, and we started using it for all of our allocators, like all of the 10 that we have. And the reason why is each one of these allocators have, by default, 0 bytes allocated. They're all using a common backend instead. Not only that, 99% of your allocations are now going to go to one of these 2 meg blocks. So it's much easier to control kind of contention. You make the allocations from the 2 meg block until it's empty. And the main thing here is that you're sharing the pool, so it's very unlikely that every single allocator would spike to the largest amount. All you need is you need enough 2 megabyte blocks in this tagged heap to be able to absorb the most reasonable amount of spike in the system as a whole, rather than the whole thing. By doing this, we got 200 megs back to our game. To just visualize it, we got our 6 worker threads. This is one of those simple allocators. It's currently got one 2 meg block called game. The little orange things are just small pieces of that 2 meg block. We got 3 fibers running on the worker threads, and they all now request memory. To avoid race conditions, you need to have a lock around the 2 megabyte block. But at the end of the day, all 3 fibers now own a little bit of memory that comes from the same block, which is tagged as game, and it will be freed in a very, very clear time during the lifetime of that frame. But we sometimes need things to go faster. What you can do is you can take and store 1 of these 2 megabyte blocks per thread. So effectively, we have 6 of these blocks stored inside of the allocator. We use the worker thread index to know which one you need to access. You can get the worker thread index. In our case, we store it in thread local storage on contended access, which means that every single job running on a particular worker thread that accesses this type of allocator can do all of its allocations completely without acquiring a single lock. That's true for 99.9% of the cases. Obviously, when you run out of memory in the 2 megabyte block, you need to go back to the tagged heap, grab another 2 meg block, but that's the only lock. And you only lock once for every 2 megs. So even if you consume all memory, that might be 500 locks in a frame. That's nothing. So this is what we use for a high volume, high performance, kind of many, many thousands of allocations per frame of really small amounts. This is the guy. So to just demonstrate this last case, we got 2 fibers running on cores 0 and 1. We got 6 blocks down below. When the allocations come in, we do not need to lock. Instead, you go in, grab one of the chunks from each one of the blocks. It might be a little hard to tell, but the colors are different right now in the different worker threads. The jobs might go to sleep, wake up on another worker thread. That is still fine, and if they do additional allocations, the allocations will go to whichever thread they're currently running on. In this case, they're running on the blue and the red one. If you think about it, it doesn't pose a problem because all of these memory allocations are coming from the same area. They're coming from blocks tagged as game, and we have a very clear time in the frame when we know we can free all of these and safely return them to the system without actually worrying about stale pointers. Yes. So to sum it up, we have a couple of things presented here today. First one is fibers are awesome. We love them. We were anticipating some rocky roads after the initial implementation, and we have actually not looked back at the job system since the shipping of Remastered. It has just worked. Frame parameters, I recommend anyone, big or small engine, it's a great way for you to deal with multiple frames being accessed. Simplifies all your gameplay programmers, or any programmer really on your team, the way they interact with data associated with a given frame. And last but not least, this tag-based allocator can be the saving grace if you're running out of memory. So thank you all. If you have any questions, please use the microphones.
Do you have any estimates on how the latency changed when you switched from a single frame processing at like 25 milliseconds to 2-frame processing at 15?
You're talking about input latency?
Right, input to final result on screen.
Yes. That is what you would expect. It's then multiple, so you have about 16 milliseconds of latency for the game, what we call the game logic stage, 16 milliseconds for the render, and 16 milliseconds on the GPU. So those are what you have, and then I guess there's a scan out that we can't do anything about.
So an extra frame compared to the hypothetical situation where you could optimize 25 to 15 without like doing 2 frames at once.
Well, you could still have this approach, but don't allow your stages to take 16 milliseconds. If you allow them to only take 8, you could reuse the same approach and have shorter latency. And this is actually still shorter latency than we had on the PS3, just because our frames are 60 hertz, or are 1/16th of a second.
Thanks.
Yep.
Do you have any recommendations for fiber libraries that aren't PS4 only?
When I looked at fibers and when I actually implemented it under Windows first, there are, in my opinion, there are so few functions, and they're actually pretty easy to wrap your head around. I wouldn't bother with a library. If you run some tests with them, you will find that you need maybe 5, 6 functions that you write yourself. The OS provides all the functionality for you, so it's more of a little wrapper fluff that you make. That would be my advice. The PS4 provides a fiber library. Not a big fan of it, so that's my recommendation.
Thank you.
Hello, I'm a programmer on Mortal Kombat, and we use fibers extensively for our gameplay. And I just wanted to make 2 notes on things you said. The TLS storage issue, that's not PS4 only. That actually happens on Visual Studio on both PC and Xbox. I have a ticket open. So TLS safety issues do occur, even if you enable TLS safe fiber optimizations. So that's a problem on there. And the other thing...
I've actually seen that because I had the problem on Windows, and I know for a fact that the fiber-safe TLS optimizations at least worked on the compiler I used.
Okay.
So it might be that they broke it.
It doesn't work on Visual Studio 2012.
Okay.
So I have a ticket open on that if you look on the Visual Studio site. But another thing, too, is if you're using Razer CPU markers or PIC CPU markers, I believe that they use some TLS stuff internally, and they go bonkers if you use them across fiber sleeps and you don't have them matching. Sorry, fiber switches without them matching.
So it's a little depending on how you use markers. In the new version of the SDK that's coming out in not too long, they have fixed that.
Okay. Well, just if you're working on them currently, there's a couple things that go bonkers.
Okay, yeah.
So a question about how fine-grained those jobs are. So you gave the example of making each sort of object animation, which I take to mean like blending the joints as an individual job. Did that run you into any issues with cache coherence? Because now you're splitting these things up and not keeping them sort of together?
Cache coherence is a really finicky thing. And especially when you start going from a kind of PS3 was okay because it was like mostly single-threaded, but when you're running 6 things at once, and in our case we're like doing all these multiple frames at once, it was a much bigger importance to fill the cores with work. We actually pay absolutely no attention to cache coherency because we found that it was more productive to make sure that the cores are at least trying to do useful work all the time rather than dealing with the cache lines, which might sound weird from us, but yes.
Great, thank you.
Hey, so I think you touched on this briefly, but I didn't really follow, so I wanted to ask again. How do you deal with having multiple stages of your frame render needing to share and synchronize data between them, like the output of one becoming the input into another? Is it frame param, or do you serialize it somehow?
So the output of one to be the input into the next stage.
Right.
Yes, that is the frame parameter.
Cool.
So effectively what we actually do at the beginning of the frame is we kick off both jobs. and one is waiting on a counter that we only set to 0 once we've filled in the frame parameters. So one stage is completely done with the frame parameter when the next stage takes over.
So can a frame parameter have a pointer into some of the 2 megabyte blocks that you allocated?
Yes.
So you don't free the 2 megabyte block from the first stage until the last stage is done executing?
No, we can free, so in every stage we actually check and we say, has a previous frame that were executing the stage completed? So we try to, the next frame will try to clean up from the frame before it. But if things are executing a little weird, it might be 2 frames until you can free it, but we're lazily freeing all of that.
Cool.
Yes.
Sure, go ahead.
Was there ever a time when stack-free fibers were like a viable optimization for parts of your code?
Stack-free fibers?
Yes.
How do you run a stack-free
They're just like
fiber?
normal fibers, but since you know you're not going to be doing any function calls, you just don't bother to copy the stack or anything like that?
There is still a tiny little bit of work that the OS does when it does the fiber switch, so I don't think, unless you would, I don't think you would be able to use that, because effectively, if I understand you correctly, you would need to make the switches of the registers yourself, but you don't have privileged access to actually change some of these registers. So no, we haven't tried that.
I was curious about between the different stages, like for the graphics stage, for example, if you go much faster and you're like 2 frame in advance, where your game logic is on the last frame, how do you deal with, is the jobs created from the game logic have a higher priority than the graphics one? So because you want to finish the current frame that you want to draw.
Yes, we definitely have that's an interesting fine balance, actually. I do believe we ended up with having believe it or not, the render logic ended up being lower priority than the game logic. And it just happened to be that we were filling in so many of the slots that there was just a tiny little bit of sliver left to be done on render logic before the game was done. But that is something that is really up to you in your game, depending on how big each section is. Being able to tweak those is key.
Thank you.
This may be a little similar to the previous question, but I was curious. You said you have the different stages, but what if you're, say you're in your render stage and the was it GPU then render? What if the GPU stage that's running, say, on frame 2 finishes before the render stage for frame 3? Mm-hmm. Do you have to wait for the frame 3 to finish so that you can then move the frame over to start executing the next frame when they start bumping up against one another?
So there is a tiny little buffer, effectively, in between the queues. So it was the other way, it doesn't really matter. So if the GPU is not done executing, but I am actually done with the next frame's render logic, I will still kick that off, but it will not be completed, or it will not start, because each stage is guarded to never, you can't have multiple stages, instances of the same stage running in parallel. So effectively what we're actually doing is we're just the second render logic stage is waiting on the counter that the first render logic stage will decrement.
All right, and you said you really had your engine running at 16 milliseconds pretty smoothly, so you didn't really come up on that little sliver that often, did you? Was it pretty tight?
It's actually very, what do you mean, the sliver of time left?
I'm assuming most of each stage was really close to running at 16 milliseconds. It wasn't oh man, suddenly this render stage took 12 milliseconds all of a sudden.
That happened, for sure. Most of the time, one of the stages can actually be a lot cheaper than the others. So we often had cases where the render stage or the game logic stage would run really fast, and it would catch up with all the other ones. And to prevent us having 16 game logic frames kind of all stacked up and you have an enormous input latency, we only allow 3 frames using our frame definition to ever be in the system as a whole. So if I start the new game logic frame, one of the first things I check is, did we actually flip the frame that was 3 frames ago? Has that actually flipped onto screen? If it hasn't, then we're running a little too fast and we need to slow down. So it kind of guards itself a little bit from going totally crazy.
All right, thank you.
Time. I will go over to the wrap-up room, number 300 after this, if you have more questions. Thank you.